Mass extinctions may explain why intelligent life is rare in the universe. On many worlds, catastrophes may wipe out complex life or completely sterilize the planet, preventing the evolution of intelligence. Earth may have gotten incredibly lucky to be habitable for 4.5 billion years. I call this the charmed life hypothesis, and it's possibly the most terrifying explanation I've ever heard for why we haven't made contact with aliens. So, why haven't we found extraterrestrial civilizations? Why does the universe beyond our solar system appear to be silent and dead? In previous lectures, I've explored this problem, the Fermi paradox. And this is the paradox. The universe is old and vast, with billions of stars. It's billions of years old. And this would seem to provide abundant time and ample space for intelligent life to evolve and to spread throughout the galaxy. So we'd expect intelligence to exist elsewhere, we'd expect to see it, but we don't have any strong evidence for it. Or as Enrico Fermi put it, where is everybody? This is the Fermi paradox. So we have no good evidence that aliens have visited us or have tried to contact us. And we haven't found alien artifacts on the Earth. We haven't found alien artifacts on the moon or elsewhere in the solar system to suggest that extraterrestrial civilizations might have visited our solar system in the past 4 billion years. We look out with our telescopes out into the darkness of deep space, and we see nothing. We transmit signals, but we receive no reply. There is only a great silence. Why? This is sometimes treated as more a problem for science fiction than serious science. It's not something that professional scientists should worry about. But I think it's one of the most profound questions we can possibly ask about evolution. How likely is it that something like us would evolve? And to answer that question, we need to be able to understand the course of events that led us to be here in the first place. How did we get here? It's hard to think of a more profound question. I've previously explored the idea that intelligent life might be extremely unlikely to evolve because the big evolutionary jumps, the complex adaptations necessary for intelligent tool users are rare. These include adaptations like photosynthesis, the eukaryotic cell, sexual reproduction, complex animal life, the bony skeleton, human-level intelligence, and even life itself. These are unique one-off events. And they also took hundreds of millions of years to evolve, so they were not easy to evolve. This suggests the fact that these adaptations are unique and took a long time to appear implies that they're highly improbable. They don't just happen every day, they don't happen often. Maybe on some planets they never happen at all, and life gets stuck on one of these big steps. So life might be common elsewhere in the universe, but it rarely evolves into species that can make spaceships and radio transmitters. So perhaps 1 in a billion worlds that has life gets to the point of evolving civilizations of intelligent tool users. So this is one possible answer to the Fermi paradox. I've also explored the idea that planets require a rare combination of characteristics to be habitable for intelligent life. Not just the right distance from the sun, although that is important. They also have to have the right chemical composition, things like phosphorus and carbon and nitrogen and sulfur and so on. They have to have the right amount of water, not too much, not too little. They have to have a highly circular and stable orbit. They have to have a magnetic field to shield the planet's atmosphere from the solar wind. They need plate tectonics to create continents and recycle minerals. A sun that's large enough to be stable, but small enough to burn for millions of years, rather for billions of years without burning out. So we have to simultaneously optimize for over a dozen different parameters. And such worlds that fit all these criteria at once might be highly improbable. Let's say 1 in a billion, and there's only a few worlds like this per galaxy. This is the rare Earth hypothesis. Today, I'm going to explore a third hypothesis, a third explanation for the Fermi paradox. And this is the idea that even when there is a suitable planet where life can evolve and start becoming complex, and even where it takes the right evolutionary pathway, it starts evolving these complex adaptations, these hard steps, and becoming more and more complex, evolving towards intelligence, this pathway may be cut short by mass extinctions, by disasters, by catastrophes, possibly even the destruction of the entire planet. And so perhaps only a handful of habitable planets will survive these disasters, allowing intelligence to evolve. And what I'm going to argue is that Earth's geological history shows a series of near misses that suggest not only that our planet is highly suitable for the emergence of life and it's been very stable for a very long time, but that it's incredibly lucky. We live a charmed life. And this is the charmed life hypothesis. But I'm going to start with another question, a completely different question. And this is the question that took me down this strange intellectual rabbit hole. And that question is, why should we explore space? In recent years, we've seen the start of a new space race. Companies are building powerful, reusable rockets that can put tons into orbit faster and far more cheaply than was possible just 10 years ago. And this, along with the computing revolution, which lets us make very small, cheap satellites, has created a new space race. But why do we need to do this? Why is space so important? Well, the answer put forward by Elon Musk, the CEO of SpaceX, is that it's existential. It is about the very survival of the human species, even of life itself. This is Earth seen from the edge of our solar system at a distance of around 4 billion miles. And you see this tiny bluish little light. And you and everyone you know live here on this tiny little blue light. And it looks incredibly small and vulnerable in the vastness of space of our universe. And if anything were to happen to that tiny little pinprick of light, nuclear war, a rogue AI, a super virus, a giant asteroid impact, intelligence might vanish from the Earth and possibly from the Milky Way. This flickering candle of sentience, this tiny light of existence peering out into the vast dark universe, goes out. And perhaps with it, all life within thousands of light years. So how do you sleep at night knowing how fragile our existence is? Well, if you're billionaire industrialist and a huge sci-fi nerd Elon Musk, the answer is simple. We colonize other planets. The idea is that we have all our eggs in one basket, that basket being Earth. So if anything hits the whole planet, we have a nuclear war, global environmental disaster, artificial intelligence runs amok. This wipes us out. We have no plan B. The only way for humanity to survive long term is to become a multi-planet species. So the basic concept behind this is bet hedging or diversification to reduce risk. A good real-world example of this would be the stock market. It is generally a terrible idea to put all your money in one stock, for example, like, say, Tesla stock. Now, I wouldn't bet against Elon Musk. Bill Gates famously did, and he lost money. He shorted Tesla and lost maybe around $2 billion. But you'd be crazy to put all your money into the company either. I'm not saying you wouldn't do well. You might even get rich, but you could just as well have everything wiped out. It is a high-risk, high-reward strategy. So to reduce your risk, what you typically want to do is you might put your money in a number of different stocks, not just the one stock, maybe bonds, gold, crypto, etc. So then it's very unlikely that everything wipes out all your assets. You haven't put all your eggs in one basket. We also see this concept applied in engineering. This is why we have redundancy, backup systems. You have multiple engines on your bomber. In case one gets hit or damaged, you can still fly. SpaceX rockets have multiple engines, so the rocket is potentially recoverable, even if one or two or even three engines fail. Warships have multiple watertight compartments, so that even if one or two are flooded, the ship can still stay afloat. So if you look at it this way, We have no backup plan. We're not diversified. In this worldview, staying on Earth is risky. Staying on Earth, where everyone is on Earth, we have all our people on one planet. It's like flying on an airliner that has only one engine. If it goes out, you're done for. Or putting everything you own in Tesla stock. Or if you're a student, not automatically backing up your hard drive. I can't tell you how many sob stories I've heard about that. My final year project was on my hard drive. I didn't back it up. Back up, kids. Duplicate all your data. Have it in 2 separate places. And in the same way, we want to diversify the species level to hedge our bets, to create redundancy. We want backup worlds. We need to become multiplanetary so that no disaster can wipe out everyone and extinguish the entire species. There's not a single point of failure. And right now we have that. And that point of failure is potentially the Earth. So we need to become multiplanetary so that no single disaster can wipe everyone out. And that's the only way to ensure that our species survives long term. At least that's the argument. Now, if this sounds like science fiction, there's a really good reason for that. These ideas sound really familiar to me as someone who read a lot of science fiction as a teenager. And I think Elon and I think we read a lot of the same books. So, for example, in the classic novel Ringworld, an alien hires humans to explore an ancient megastructure. It's a giant ring of super strong metal. It is the diameter of an Earth orbit that is spun to create gravity. It's an artificial world. And the reason the aliens and all the other species are so interested in the ring world is the galaxy's core has gone supernova. All the stars have blown up. And there's a blast coming, traveling at the speed of light, that will arrive in 50,000 years and kill everyone. And this is the only place on the edge of the galaxy that's far enough away and also large enough to accommodate everyone, because the universe is basically a galaxy is blowing up. So space travel in this novel is necessary to preserve the human species. So this idea of leaving Earth to escape catastrophe is straight out of a sci-fi novel. So is Elon a visionary, a charlatan, a genius, crazy, a kid who liked sci-fi and never quite grew up? I don't know. Pick one, maybe all of these. But this is the stated purpose of our new space program. And this is why we're building rockets. And of course, the billions of dollars of profit might also have something to do with it. But hey, why can't you make a good profit and save the human species? Why do these things have to be mutually exclusive? It's kind of a twofer, right? So I started thinking about this. I don't know. I just thought it's an interesting argument. If it's wrong, why is it wrong? And I started thinking, is this really the best way to ensure our species survival? And I started thinking, well, probably not. Does it really make sense to move to Mars? And I don't think it does. At least this is kind of the argument. This is how the argument I started developing. So if you think of human colonization on Earth, it's not really a good analogy for space colonization. Because when we were colonizing the Earth, wherever we went, we found the conditions we needed to thrive. We had ambient temperatures, we had water, we had food, we had the Earth's magnetic field to protect us from radiation. We have all these things. So when the Polynesians are sailing across the Pacific thousands of years ago, they find a tropical paradise. They're sailing these islands across Polynesia. There's coconuts everywhere. You plant taro and breadfruit, and you get more taro and breadfruit. You pull tuna and swordfish straight out of the sea, fresh seafood. So the fundamental problem of a habitable environment is already solved. And that meant that the Polynesians could colonize this habitat with literal Stone Age technology. They're using wooden canoes and stone axes. These are the greatest explorers in history, perhaps, but they're sailing from Indonesia to South America across the Pacific, doing it with relatively simple, literally Stone Age technology. And they could survive in these environments because it produced everything they needed for them. Now, none of this is true of Mars, obviously. You're starting from zero. Forget tropical beaches and coconuts. You don't even have oxygen there. So Mars just isn't very habitable. The surface is cold, there's no oxygen, there's virtually no atmosphere, very little water. Because the atmosphere is so thin, liquid water will just boil away. It can't exist on the surface. The gravity is low. It's unclear what the long-term effects on human health would be. Can we successfully, live and reproduce in this low gravity environment? There's no ozone layers. The surface is bathed in ultraviolet without a magnetic field that's subjected to cosmic rays. Nothing grows there. This is a very hostile environment. You may have noticed. It's not just hostile. Mars is less habitable than the most uninhabitable places on Earth: the Sahara, the Atacama Desert, Antarctica, the Himalayas. Meanwhile, Earth is highly habitable. Earth has normal atmospheric pressure. It has normal gravity. It has oxygen. It has warm temperatures. Water is everywhere. And there are animals and plants to eat, and they just grow like magic. Just put seeds in the ground, and you get, fruit trees and grain and corn and all this stuff. And the thing is, even its most difficult, it's still more habitable than Mars because it has all these things. But here's the key thing, and what I think is the interesting argument. It always has been. It's always been this way. If we look back through the fossil record, we see that life has been around for an incredibly long time. We have dinosaurs and ammonites existing 100 million years ago. We have trilobites 500 million years ago. Cyanobacteria 2.5 billion years ago. And life itself probably goes back around 4.5 billion years ago. Earth has been habitable to life for literally billions of years. We have no evidence that Mars has ever had life. It's possible it did, but we don't have any strong evidence to that effect. So here's the thing. At pretty much any point in Earth's history, you'd be much better off here than on Mars. And it's not just this long history of habitability, it's an unbroken period of habitability. I mean, think about that. Life's history goes back about 4 billion years or more with no interruption. We can build molecular phylogenies showing an unbroken chain of descent linking us to, primitive eukaryotes and bacteria and archaeans going back 4 billion years to the last universal common ancestor, descent with modification for billions of years. Life is like this eternal flame, a fire that's been kept going, passed on from one species to another. The processes of life have kept going since the dawn of life. A fire kept going for 4 billion years, and it's flickered, but has never once gone out. Earth has been habitable continuously, even through severe global mass extinction events. Historically, 5 major mass extinction events have been recognized, but as the fossil record has improved, we've recognized maybe about 24 in the past 500 million years. One of the best known of these extinction events is the end Cretaceous mass extinction that wiped out the dinosaurs. An asteroid hit the Yucatan Peninsula 66 million years ago. It shoots dust high into the atmosphere. It blocks out the sun. And the world grows cold and dark, and plants die, and the dinosaurs either starved or froze to death. But there was still air in normal Earth gravity, and temperatures were warmer than they were on Mars. And so many animals survived. Alligators and turtles and fish and birds and frogs and salamanders and mammals, our ancestors. Think about that. Earth after an asteroid impact is still far, far more habitable than Mars. There's a quote by Larry Niven, who wrote Ringworld, and he says, "The dinosaurs went extinct because they didn't have a space program." Really? Is that why they went extinct? Or rather, the point being is is that the only way to survive is a space program? Because after all, crocodiles and paddlefish and mammals all survived, and they didn't have a space program. Curiously, Niven actually wrote another science fiction novel, Lucifer's Hammer, about people surviving a common impact on Earth. So it kind of argues his own thesis is wrong. You don't need a space program to survive the asteroid impact. I mean, think about it. You could probably save most of the human species if you just had a few years warning about the asteroid. I mean, most of the food we grow doesn't even go to feeding people. It goes to cattle and pigs and chickens. So if we all just went vegetarian for a few years, I know that sounds like a terrible, terrible thing, but okay. We divert these crops into massive granaries. And so we have huge food supplies to survive a period of low photosynthesis. We could then build large underground bunkers where people could shelter against the impact of the asteroid, the fallout, and the cold, like in the movie Doctor Strangelove, if you've seen that. We could probably need some sort of fuel to keep these bunkers warm. Coal is abundant, but nuclear power would be another great source of energy. Or maybe you could build big ships that would carry lots of people and food for a few years. Convert aircraft carriers into arcs. They'd be highly defensible and able to move about as climates changed and take advantage of changing conditions. Now, I'm not saying this would be easy. Probably a lot of people die, maybe billions of people. There would be wars. But it would be a hell of a lot easier to shelter in place on the Earth to survive an asteroid impact than trying to move into Mars. Again, it's a lot, even after that asteroid impact, Mars is going to be a lot more hostile. We can look at other extinction events. One of the biggest extinctions that we know of in the fossil record is the Permo-Triassic extinction event, 252 million years ago. It is among the worst extinctions in Earth's history. Upwards of 90% of all species on the planet disappeared, but enough still survived to rebuild the ecosystem. And it is thought to have gotten really hot. The seas became anoxic and acidic, and the ozone layer broke down. But, well, I mean, could you survive that? Well, okay, it gets really hot. You move to Greenland or Antarctica. You install air conditioning. Oh, the ozone layer breaks down. Well, get sunscreen. Again, it wouldn't necessarily be easy, but it'd be a heck of a lot easier surviving here during a massive volcanic eruption like the Permo-Triassic event than surviving on Mars. If we go back 650 million years ago, Earth is in the grips of a global glaciation. For 20 million years, ice sheets extend down to the equator, turning Earth into an ice planet, a Snowball Earth. And then 700 million years ago, we have an even longer glacial event, a Snowball Earth event lasting 50 million years. And yet there was still air, at least some oxygen, normal gravity. Could we survive this? Actually, this is the easiest one. What you do is, the environmental groups are going to hate me for this, but what you do is you drill down into some oil fields, you let the oil spill out in a big gusher, you set it on fire, massive CO2 spike, global warming, ice age over. This would be highly solvable. Again, this would probably, it's maybe not quite that easy. It's a bit of an engineering feat, and geoengineering probably isn't easy, but it's probably easier than space travel. If we go back 2.5 billion years ago, when the great oxygenation event fills the air with oxygen, but before then, there's basically no oxygen. But, there's still an atmosphere, there's habitable temperatures, there's normal gravity, there's oceans of water. A planet like this would be more challenging to survive on without oxygen, but again, it's still easier than Mars. So if you go back 4.5 billion years, Earth has been the most habitable planet in the solar system. And in fact, habitability has increased over time, and species richness has continued to increase over the 500 million years. It's become more and more habitable to life. So given that Earth has been habitable for 4.5 billion years, why do we need to worry so much? And why assume that moving to a small, barren, hostile world like Mars would ensure survival? We have this very stable, safe environment. It's kind of like being in the middle of an ocean on a cruise ship and then jumping off the cruise ship because you're worried the cruise ship might sink. Well, I don't know. It's been pretty stable so far. Why not stick with it? So this is the counter argument to the we need to become multiplanetary argument. So is it the case that people talking about space colonization are just reading way too much sci-fi? And this whole idea of making the human species multiplanetary is nonsense, right? Because the Earth is safe and stable, right? Well, not so fast. I thought this was a really clever argument when I came up with it, but I always like to play devil's advocate and say, okay, but what about this? Or what about that? Have you considered this? And I stopped and I thought about this and I said, is it really the case that Earth is so stable and safe? it's inherently a safe place to be? Or is it just lucky? And I started thinking, like, maybe in assuming this history of habitability is normal for our planet, we might be falling prey to survivorship bias. So, investment banks have this line that they give to their customers. They say, past performance is no guarantee of future results. And this is so that you don't get sued when you lose all of your money investing in their mutual funds or putting all your money in Tesla stock or whatever. Now, a good example of this, where past performance doesn't predict future results, is certain managed funds. They do well for a while, then maybe you buy into this managed fund that's gone up a bit, and then our mutual fund goes down. And what it turns out is that it wasn't actually like well managed. They were just kind of on a lucky streak, and it's reverting to the mean. And they've done studies, and that for the vast majority of people who pick stocks, who are paid to pick stocks by these, investment banks, their performance is indistinguishable from random. You do about as good picking stocks at random, just throwing darts at a board with names of stocks and companies on there, or have like a monkey draw names out of a hat, as using a professional stock picker. So what happens is you hire 100 guys to manage mutual funds, and they all pick stocks, or you have 100 monkeys pick stocks. And the top 10 stock pickers, the top 10 monkeys, are going to make a bunch more money than average, the rest of the market, just by chance. They'll be lucky outliers. Then you buy their funds and they crash. I'm like, what the hell? You stupid monkey. You put everything in Tesla. I want my money back. And the bank says, well, we told you. Past performance is no guarantee of future results. So this is an example of, you can't assume that just because something has done well for a while, that's going to keep doing well. There's a logical fallacy in gambling. It's called the hot hand fallacy. And it's the idea that because you've won in the past, you'll keep winning. It's this idea of winning streaks. So let's say you go to the casino and you play roulette and you're having just this amazing night. Every once in a while this has to happen to somebody, right? Well, maybe it happens to you. You bet on black and you keep doing that and you double your money over and over and over again. And after a number of spins of the wheel, you've done this 10 times in a row, you've won $10 million in a night. Should you keep going? Now, assume for the sake of argument the game isn't rigged, although that would be a possible explanation for why it keeps hitting black, but it's not in this scenario. You've just won 10 times in a row, you've won $10 million, should you spin again? Well, think about it. What are the odds that you lose it all 10 million, because you're betting everything every time on the very next spin? 50-50. The fact that you had a good run doesn't affect the odds going forward, and you could apply the same argument to the Earth. Like, you've had a pretty good run, but could that just be chance? How do we know that on the very next spin of the wheel, the next roll of the dice, we don't lose everything? So in the same way, we have to consider, is this long-term habitability a real trend that we can extrapolate onto the future? Or is our planet on a lucky streak, like a gambler at the table in Vegas, or a mutual fund manager who's just picking at random and happen to do unusually well? He's that outlier. And the next spin of the wheel, the next roll of the dice, the next earnings report, we lose it all. Are we just playing cosmic dice here? So is the Earth safe or just lucky? Are we playing planetary Russian roulette with the fate of the human species by staying on Earth? So I started thinking about this, and I thought, well, okay, let's look back at Earth's history, and we see this unbroken period of habitability. That can't be chance, right? What are the odds that we just happen to end up on the planet that's been flipping the coin for 4 billion years over and over and over, and it always comes up heads? But consider, how could it be otherwise? If hypothetically, most planets are unlucky and don't make it for 4.5 billion years, and only a handful, 1% or a fraction of 1%, make it this long and remain habitable, where else could we evolve? Where else could we find ourselves except on one of these rare, lucky planets where everything worked out? So I started thinking about a book I read a few years ago when I was traveling. It was kind of one of those books that encounter randomly while traveling, and it was a really interesting read. And it was a book called The Pacific War Diary, and it's really a remarkable book. It's the diary of a sailor serving in the U.S. Navy on the USS Montpelier, a cruiser that fought in World War II in the Pacific Theater. And Montpelier fought in the Solomon Islands, where it served as a flagship of the fleet. It fought in Saipan and Tinian, where they take the airfield that would be used by the Enola Gay. They fight in the Philippines, the Battle of the Leyte Gulf, and they finally support operations around Japan. So it has a really remarkable history. And what's really striking about this book is that throughout the war, the Montpelier has a series of near misses. There's this incident where they get a little too close to this Japanese shore battery, misjudging the range of the Japanese guns. And the Japanese start splashing shells all around the ship. They're within range. The captain quickly tells his crew, let's get the heck out of here, a little sheepishly. Off of Okinawa, the Montpelier is hit by two kamikazes, but they fail to do any major structural damage or hit anything really vulnerable like the magazine or the engines, so she's able to continue on. And there's this incredible battle in Papua New Guinea, and American and Japanese ships are dueling it out in the middle of the night, and the flash of their guns lighting up the darkness. And this is one of the last great ship-to-ship battles in naval history. And the Montpelier takes a Japanese torpedo directly to the bow. There's this huge clanging thud as the torpedo makes a direct hit on the bow, and this long, terrifying silence. What happens next? Nothing happens. It's a dud. But what else could happen? So what happens at the end of the book? Well, Montpelier and the author both survive. But think about it. How could it be otherwise? If the ship had gone down, we wouldn't have the diary. I couldn't have picked up that book and read it. You couldn't order it off of Amazon. But there are, of course, countless ships that didn't make it, and diaries that would be on those ships that went down with them. And these ships were taken out by Japanese torpedoes, they were taken out by dive bombers, they were taken out by kamikaze planes, by suicide submarines, they were wrecked on reefs, they were sunk in huge cyclones. Thousands of US warships and merchant ships were lost, and thousands of Japanese ships. 500,000 American, Japanese, British, and Australian sailors would drown in World War II. And we don't have their diaries. So when we study winners, the survivors, we get a biased picture. In World War II, they studied bombers returning from bombing missions over Germany. And what they saw was lots of damage to the wings and the fuselage and sometimes the tail, but relatively little to the engines or the cockpit. So the naive approach would be to look at the areas that have lots of bullet holes and saying, well, they keep shooting up the wings. We need some heavier armor there. But since the damage should be more or less randomly distributed across the airplane, if it's hit by a flak burst or, they're just spraying machine gun bullets at it, that raises the question, well, why is the damage so concentrated? Why aren't we seeing damage in the cockpit and the engines? Where are all the bullet holes and the shrapnel damage in our engines and the cockpit and these other critical structures? And the answer is that those bullet holes are in the planes that didn't make it back. We have a biased sample. Huge numbers of aircraft were shot down or crashed or suffered mechanical failure over Europe and didn't return to base. And we are simply seeing the surviving aircraft. So the real damage, or rather the real danger, is in the damage you don't see. You rarely see damage to the engines or the cockpit because those bombers never come back, they never return. The bullet holes and the shrapnel damage we don't see tells you where the danger is, where the threats are. Hence, survivorship bias. You study survivors and you get a biased picture. What I'm arguing is Earth itself is likely subject to survivorship bias. Looking, for example, at a map of impact structures on the surface of the planet, you'll notice that we do not see any truly catastrophic impacts. That might sound a little crazy when it's like, wait, Chicxulub, right? That killed the dinosaurs. Yeah, but like, males survive. We're still here, right? It actually allowed us to evolve and become intelligent. So the biggest impact we see is the Chicxulub impact in the Yucatan, which is about a little over 100 miles in diameter. But we don't see any impacts in the past 100 to 200 million years that are 200 miles in diameter or 500 miles in diameter, which would release 10 or 100 times more energy. Probably because if there had been any impacts that severe, it would have just wiped out all terrestrial life, all complex animals on land, and we wouldn't be here. Earth can't have the equivalent of a direct hit to the engines or the tail shot off, or we just wouldn't exist. So, where is the missing damage? It's in these other planets that didn't make it, that didn't evolve intelligence. And they don't look out into the universe and wonder, where is everybody? So, seen in this way, mass extinction events seem less like these world ending catastrophes than near misses. It's like getting a few bullet holes in the wing. And it may sound a little crazy to say that the end Cretaceous and end Permian extinction events weren't that severe. But we're here, aren't we? We made it. They weren't that bad. I mean, come on, suck it up and deal. It's been 66 million years already. Get over the extinction of the dinosaurs. It wasn't that bad. Uh, but yeah, it's kind of a crazy way to look at the universe that, these events, maybe it could have been a lot worse than it was. If you prefer, we could look at the layers of the rock record as being like the pages of a book. And the fossils in these strata in these are the writing on these pages. And we look back at this book, The History of Life, and we see that there are no real disasters, things that completely wiped out life or wiped out complex life, but a series of near misses, much like we see in the Pacific War Diary with the Montpelier, and how it's full of near misses by kamikazes and non-critical damage and dead torpedoes. And in the same way, that book, the Pacific War Diary, has to end with the ship surviving. Our history, our geological history, has to end with us emerging. If the book written by the rock record is our history, the ending is written. We know what the ending is. We pick up the book. You're reading it now. Everything must lead up to this moment. It's a bit like an action movie franchise where you can't kill off the lead character because there's already a contract for a sequel. John McClane from Die Hard can't die. You cannot kill Batman. They're gonna make it. They have plot armor. So it follows that the worst events we see in the fossil record have to be non-catastrophic. They can be damaging, but they must be survivable. Earth is like one of these bombers that took huge hits over Germany and took out big chunks of the tail or the nose, but they missed anything truly vital. And that makes you wonder, what would a really bad extinction be like? This is the equivalent of a direct hit from anti-aircraft artillery taking out your pilot, your co-pilot, and the cockpit levels of bad. So what would that be like? So is this hypothesis correct? Well, imagine a universe in which severe mass extinctions are common. And most habitable planets will either see complex life wiped out or life completely extinguished by sterilizing events. What do the surviving worlds that evolve intelligence look like? In a very dangerous universe where there's lots of catastrophe and mass extinctions, the handful of planets that survive will show multiple non-fatal hits, the equivalent of holes in the tail of a bomber or a near miss by a kamikaze on a ship. There will be a series of lucky breaks and near misses, disasters, but none so disastrous and so catastrophic as to wipe out life entirely. Which is exactly what we see in Earth's history. It implies that we may be witnessing cosmic survivor bias. But if Earth is like the Montpelier or a surviving bomber, we could study the shipwrecks and the crash bombers to understand what might destroy planets. Now, of course, we have no formally inhabited worlds to study. We can't find a planet where, oh, they got almost all the way to intelligence, then big asteroid. Nothing like that exists. But what we can do is we can look to see if some of these world-ending catastrophes might befall uninhabited planets. Even other planets within our solar system, we could look at them and study them and say, okay, well, it's like kind of like, yeah, it's just look for bullet holes in other planets, so to speak. Almost every body in the solar system, including the Earth, rotates counterclockwise. They all rotate in the same direction. It comes down to how the solar system formed. And that means that on these other planets, the sun also rises in the east, and it also sets in the west. There's an exception here, and that's Venus. Venus rotates in the wrong direction, not counterclockwise, but clockwise. And what that means is that on Venus, the sun rises in the west and sets in the east. How is this possible? Well, one of the leading hypotheses is that there was a massive impact early in Venus's history, and it reversed the spin of Venus. So here we have evidence for an ancient catastrophe, potentially world-ending type event. Uranus is tipped over, so the North Pole actually points to the side and actually slightly down, slightly to the south. And again, this is thought to be the result of a massive impact. And it must have been, something truly massive to tip the entire planet over. If we look at Neptune, it's got another peculiarity. So one thing is a lot of the outer planets have lots and lots of moons. Neptune has just one moon, Triton, so that's already a bit odd. But here's the really odd thing. It orbits backwards. So again, all planets orbit, just like planets spin counterclockwise, moons orbit counterclockwise around their planets, and planets orbit counterclockwise around the sun. But Triton, Neptune's only moon, goes the other way. It goes clockwise. It orbits backwards. How is that possible? Why does it do that? And the theory is that Triton didn't actually form as part of the Neptunian system. It's a captured ice dwarf, and when it entered orbit around Neptune, the gravitational interactions with the other moons destroyed them. Some were thrown into space, and some were probably thrown into Neptune itself, and it must have been an incredible catastrophe having an entire moon crash down into your planet. Another example of catastrophe is the rings of Saturn. Now, Saturn is unusual in having rings, and the reason why is that rings just don't last very long. They're not a persistent feature. They slowly degrade over hundreds of millions of years and just sort of fall out of orbit, the little particles. So other planets are thought to have had elaborate ring systems in the past and then lost them. Earth, for example, briefly had rings after the collision that created the moon. So Saturn's rings appear to be a geologically recent phenomenon. The fact that it has them tells us they formed quite recently because they can't be that old, and they might be around 100 million years old or so, which would mean that the rings of Saturn are younger than Brontosaurus and Stegosaurus. And, they've been around, alligators have been around longer than the rings of Saturn. And they're thought to be formed by the breakup of one of Saturn's moons. So this is not an ancient catastrophe, but a geologically recent catastrophe. So looking throughout the history, our solar system, we see a heck of a lot of catastrophe. And some of this is thought to have occurred quite early, before life would have formed on Earth. But some of these events, like the rings of Saturn, show that you can have catastrophes occurring relatively late in our solar system. But probably the most remarkable example of a catastrophe in our solar system is something we don't even see at all. And that's because it appears that at least one planet was lost in the formation of the solar system. So people have tried to model the formation of the solar system, and they have a huge problem trying to get something that looks like our solar system with our arrangement, configuration, and number of planets if they start out with the same number of planets we now have. And if they want to get something that looks like our solar system, the only way they know how to make this work is they add in another planet as our solar system is forming, and this planet is out beyond Saturn And then interactions between it and the other planets cause it to be kicked out of the solar system. And then the simulations produce something that looks something like what we have now. So a planet formed early on and then was ejected from the solar system. Planets can simply be lost. They can be thrown out of the solar system, thrown into another planet, or thrown into the sun. So it raises a question, could it have gone a different way? And it turns out these simulations, they show that the process of planet formation, solar system formation, is incredibly chaotic. That is, very small differences in the starting conditions, kind of butterfly effect, can result in radically different outcomes. And in a high percentage of simulations, you don't end up with an Earth-like world. Instead, that Earth-like world is destroyed. It's destroyed by collision with another planet, it's thrown into the sun, or it's ejected into deep space and it becomes a rogue planet. And usually this happens fairly early, before life would have appeared on the Earth. But in some cases, it can happen hundreds of millions of years, or up to almost a billion years after the solar system forms. And this would be after the emergence of life on Earth. So it is possible that on many planets, they might get to the level of RNA and DNA, or whatever the equivalent is on that planet, and evolve cells and start evolving photosynthesis. And then the planet is just destroyed. It's thrown into the sun, it collides with another planet, or it's thrown into deep space. And with slight differences in our history, if the, just very subtle differences in the formation of our solar system, that might have happened to the Earth. So we see a lot of evidence of catastrophe when we look at other planets and we look at the structure of our solar system. But some catastrophes might be things we don't see evidence of in our solar system, because if they had happened, we wouldn't be here. So we might want to look beyond the solar system and look at catastrophes in the universe more broadly. And what might that look like? So one possibility is supernovas, is that in close proximity to a habitable planet, supernovas would bombard the atmosphere with enough radiation to destroy the ozone layer and muck up the atmosphere. And the odds of this happening seem to be fairly low, at least in our part of the galaxy, because stars are just not packed that tightly. But this might be a major threat in the core of the galaxy, where stars are much more densely packed. And here, supernovas might happen nearby, close enough to be dangerous, something on the order of every 10 or 20 million years. So these events might not be totally world-ending and say, okay, well, it's breaking down the ozone layer or whatever. But if they're happening repeatedly, not like one supernova every billion years, but every few tens of millions of years, you're repeatedly having these mass extinction events, that might exert a strong influence on the evolution of your planet, and it might be more difficult to evolve intelligence. Another threat comes from rogue stars. And most stars orbit the center of galaxy, and they're orbiting in sync with all the other stars. They're kind of moving together like a school of fish, circling this big school of fish. However, a few stars have been knocked out of orbit, and they travel across the paths of other stars and can interact with them. And these are rogue stars. Now, the odds of a star actually colliding with another star or a planet are vanishingly low. Space is mostly empty space, surprisingly enough. It's really big. It's really, really, really big. And so it's very hard to hit something. Even something the size of a star, you throw that through a galaxy, it's unlikely to hit anything because it's mostly empty space. But the trick is that a star doesn't actually need to hit to cause damage to a planet. The reason is the gravitational interactions, the tug of that star on a planet as it goes by, can be catastrophic. The gravity of rogue stars can destabilize orbits. Simulations suggest that a close encounter between our solar system and another star could destabilize the Earth-Moon system. And a number of different catastrophic things could result from this. One is that the moon is destabilized and crashes to Earth. This would basically melt the entire surface, boil all the oceans, and extinguish all life. Another possibility, maybe not quite as catastrophic, but still pretty bad, is that Earth could be launched into a more elliptical orbit. That doesn't sound that bad, right? Well, the problem is that orbit would slingshot it out past the orbit of Mars in the habitable zone, freezing Earth part of the year and then plunge back in. So this kind of freeze thaw, extremely severe cooling followed by warming. It would probably make life, probably bacteria could survive underground, but unlikely, civilization could survive that. Another possibility is that Earth is knocked out of orbit and spirals into the sun and burns up. Another possibility is that Earth is captured by the rogue star to become part of the rogue star's solar system and just kind of continue its journey across the galaxy. And another possibility, kind of one of the more, I don't know, kind of strange, sad, lonely, terrifying possibilities is that Earth could simply be ejected from the solar system. A star could come by, this could happen in 100 years from now for all we know. Star passes the Earth, knocks us out of orbit, launches us into deep space, and the surface would slowly freeze as we got further and further from the sun. And things would survive. The oceans would ice over. Fish would survive under the ice for a while. Things would survive around deep sea events. Eventually, the oceans would freeze solid. And then bacteria would survive deep underground. But that would be it. And Earth would just kind of, cruise like a ghost ship through space for millions or billions of years. And again, this is probably quite unlikely to happen in our part of the universe. They've estimated the odds of this happening in the next billion years. In case you're a little scared, just take a breather. It's okay. You can pause the lecture. The odds of this happening are something like 1 in 1,000, like less than 1% in the next billion years. This doesn't happen very often, at least in our part of the solar system. But you get into the inner part of the galaxy where stars are packed much more densely, and the odds of this happening go up by orders of magnitude. And so something like, in a billion-year interval, you have about a 25 or 30% chance of a passing star coming close enough to your solar system to disturb it. That's kind of like, that's like Russian roulette. Actually, Russian roulette's more like 1 in 6. That's pretty bad odds, 1 in 3. And then over 4 or 5 billion years, you have several passes. So you have something close to a 90% chance of a close encounter with a star destabilizing your solar system if you're in the tightly packed core of the galaxy. So human lifespans are short. The timescales we think of, or we think in, are very short. Recorded history goes back a few thousand years. So we can compare historical documents and see processes happening over thousands of years. But over a human lifespan or these time span of an empire or recorded history, the movements of the planets and the stars seem incredibly boring and predictable. And the ground beneath our feet seems stable. But the existence of these tilted planets, of retrograde orbits and retrograde rotations, planet gaps, missing planets, all indicate that our solar system's history is one of chaos and destruction and instability over billion-year timescales. And it's these billion-year timescales that we're interested in for the evolution of intelligence, because it takes billions of years. Now, most of this chaos, most of these catastrophes, most likely disasters, seem to peak fairly early on before life originates. But the risk doesn't vanish entirely after life forms. And a non-trivial number of worlds may be extinguished after life begins to evolve, especially in the inner part of the galaxy. So we are probably less vulnerable out on the edge of the solar system, but some of these catastrophes may make the galactic core uninhabitable. So let's assume for a moment the charmed life hypothesis is correct. Extinctions wipe out complex life or all life on most planets. What are the most likely drivers? Well, we can extrapolate from what we see on Earth and beyond. So most mass extinctions are driven by volcanic eruptions. These include the Triassic-Jurassic extinction, the Permo-Triassic extinction, the late Devonian events. So it is possible that on other worlds, volcanic eruptions are just more severe, wiping out complex life, and we just got lucky here. Ice ages drive mass extinctions as well. For example, there's the Eocene-Oligocene event, the cooling event that causes a pretty severe extinction. There's cooling associated with the late Ordovician, and the Snowball Earth events must have caused major extinctions. But maybe on other planets, ice ages are more severe and they last longer. Imagine a snowball glaciation lasting for 500 million years. Or imagine that the snowball glaciation just never ends. It freezes solid, and that's it. Global warming is also associated with the number of extinction events. It seems to drive minor extinctions across the Paleocene and Eocene boundary. Warming is associated with extinction at the Cenomanian-Turonian transition and the Permo-Triassic event. So it might not be the only thing driving these extinctions, but it appears to be at least one major important factor in these extinction events. Now on Earth, we have negative feedbacks. These are things like silicate weathering that help pull carbon dioxide out of the atmosphere when concentrations go up. And they've been stronger than the positive feedbacks, like methane release from the permafrost, that would tend to accelerate warming. So on our world, these feedbacks have won against global warming and kept it from getting so severe. But maybe on other worlds that didn't happen. Maybe there were positive feedbacks that once things got warmer, it caused it to get even warmer, and this kind of doom spiral, pushing the worlds into a runaway greenhouse effect that kills complex life. So we look back and we see Earth managed to escape the global ice ages of the Snowball Earth era, but maybe on some planets that just doesn't happen. We haven't seen runaway global warming destroy the planet on Earth, but if that had happened in our history, we wouldn't be here. So maybe we just got lucky. Looking back over time, the climate system looks like it's self-regulating. It gets cold, so CO2 builds up and melts the ice. It gets warm, the CO2 is pulled out. But maybe it's a lot more random than it looks. Maybe we just kind of got lucky that it never quite got really cold or really hot and just kind of narrowly stepped back from the precipice. We just kind of never drew the wrong cards. And maybe it's not that Earth is stable. It's just kind of got lucky with these climate events, that they never really got out of control. Another possible driver of extinctions is that the impacts we see, they might have been much more severe on other worlds. And I think an interesting possibility might be late impacts, something on the scale of a Chicxulub event, but an order of magnitude or 2 orders of magnitude larger, that would wipe out complex life rather than allowing mammals to survive, as happened 66 million years ago. Another possibility is that the extinctions could be much more severe early on, when there's just a lot of debris left over from the formation of the solar system. So Earth experiences a period called the Late Heavy Bombardment 4 billion years ago, and this is responsible for the cratering of the moon. And Earth is repeatedly hit by massive asteroids, many times the size of the Chicxulub impactor. And these might have, sterilized entire seas, but they weren't sufficiently intense to wipe out life entirely. But can we imagine another scenario where maybe this bombardment event was able to wipe out all life? So instead of a late heavy bombardment, it's a late heavier bombardment. It's a late heaviest bombardment. And it just completely wipes out early life and leaves Earth sterilized. Another interesting thing to think about is a biogenic mass extinction. That is, life driving the extinction of life and preventing complex life from emerging. So we have a biogenic extinction event, or most likely did, with the Great Oxygenation Event. So cyanobacteria, these bacterial algae, dump massive amounts of oxygen into the atmosphere, into the oceans, and this would have driven a major extinction of oxygen-intolerant microbes. Most microbes couldn't handle oxygen, and they just died out. Now, on Earth, this ultimately, makes complex life possible. It made Earth more habitable. And there's this hypothesis called the Gaia hypothesis, and it says that life makes the planet more habitable for life, that basically life is a terraforming process that makes it possible for life to become more diverse, more abundant, more complex, bigger, and more intelligent. And you think about this, like life has made the planet more habitable. Well, it's kind of like, kind of duh, it sort of has to. What if it had gone the other way? What if there's a species of algae that evolved that made everything super toxic and it poisoned the entire planet for everything except itself, and just there's this green slime and everything else is wiped out? If there was an algae that evolved that decreased habitability instead of increasing it, well, we wouldn't be here. So only on planets that become more habitable over time could we possibly appear. We have a sample size of 1, the Earth, and we look back and draw this trend line and say, look, it got more habitable over time. Well, it had to. It's not done by a sample. We can't assume that it always goes like that on every planet. Maybe on other planets, Gaia hypothesis doesn't apply, and life emerges that frustrates the evolution of more complex life. So again, the kind of things that might wipe out planets or prevent the evolution of complex life are kind of hard for us to imagine because by definition, they didn't happen here. You've kind of got to think about something that, just didn't happen. And then it's kind of like, it sounds a bit crazy. Yeah, sure. We don't see anything like that in Earth's history. Well, exactly. But yeah, it's kind of hard to wrap your head around. A major driver of the destruction of habitable planets might be planetary instability, these interactions between planets. They tug on each other and throw each other into other planets or out of the solar system or into the sun. And if we look at our solar system, what we see is an unstable early history with all these big impact events and lost planets, but then it settles down at these relatively, a system that has these very circular orbits. It's very stable, and these planets have just been kind of going around for billions of years, not kind of minding their own business. If we look at outside the solar system, however, at exoplanets, what we see is that almost all the exoplanets we can find have orbits that are more eccentric. That is, they're more elliptical and less circular than ours. And this is pretty strong evidence that a lot of other planets have much more destructive histories. And some of these histories, again, might kind of make their planets uninhabitable before life could even evolve. But it raises the possibility that in general, the evolution of solar systems is more chaotic than ours. And probably a non-trivial number of those evolutions involve habitable planets being destroyed by these planet-planet interactions, just thrown out of the solar system or thrown into something else. So lots of Earth-like planets might form, start getting partway to evolving intelligent life, and just be destroyed. And if we look back at our history, supernovas and rogue stars don't seem like they're major threats based on what we can see in our part of the solar system or our history. But again, the most dangerous things might be these things we don't see in our history. The rate of supernova encounters and rogue stars seems to be low in our part of the galaxy, but they might be orders of magnitude more common in the core, where stars are very densely packed. You have a supernova every 10 or 20 million years, the core. Again, Earth has less than a 1% chance of encountering a rogue star in the next billion years, but that might be about 30% every billion years in the core. So much higher chances of having your planet destroyed. And so it might not be a coincidence that we find ourselves on the edge of the galaxy and not in the center of the galaxy. That could come down to supernovas and rogue stars and star-star encounters. So all this raises a really interesting question. What is the role of extinction and catastrophe in our history? And I've mostly discussed mass extinction as a bad thing, something that life must avoid. And, well, that seems bad. I mean, that seems obvious. Like, what could be worse than dropping an asteroid on the planet? But that kind of raises a bit of a question. If extinction is so bad, why do we see it at all in our history? Why do we look back and see disaster and not just a peaceful history? And I can think of two hypotheses. The first is just that our universe is a dangerous place. It is therefore almost impossible to avoid catastrophes. So, in the same way that a large proportion of surviving World War II warships suffered some damage, lots of surviving bombers that came back from their bombing runs over Germany had bullet holes in the wings. A large proportion of planets where intelligence emerges will show a history of mass extinction. Now, there might be a few that are just incredibly lucky and have no mass extinction, but they're vanishingly rare, like 1%. And 99% of the worlds are going to have a history of mass extinction. So where are we likely to find ourselves? On those common worlds with mass extinction, not that 1 in 1,000 worlds that has virtually none. So yeah, we're far more likely to show up on a planet that has battle damage, just because planets that don't are incredibly rare. I mean, if you think about it, most people have been, race car drivers or pilots for a long time. Have probably had one or two close calls. The number who've never had anything go wrong is probably pretty small. And, everybody gets a few scars or a few broken bones or two if you live long enough. Mass extinction is just the scars of living in a dangerous universe. So that's one possibility. The other possibility is much more interesting. So we see something really curious studying mass extinction. And what we see, there are these big drops in diversity as a result of the mass extinctions. And then in the aftermath and the recovery, life becomes even more diverse than it was before. What it appears is that a short-term loss in diversity leads over the next tens or 100 million years to an increase in diversity afterwards. What's going on here? Well, it may be that mass extinctions kind of shake things up, and reducing diversity creates all these open niches. So it allows species, the survivors, to move into these new niches, to explore them, and it leads to new innovations. Just like how you get, horses, bats, and whales, and primates. You get us after the dinosaurs go extinct. And yet dinosaurs after the mammal-like reptiles go extinct at the end of the Permian. So extinctions seem to actually spur innovation. So maybe a degree of extinction is actually helpful in spurring the evolution of complexity and diversity. So we can imagine variations in the level of intensity of extinction. We can have low levels of extinction, very high levels of extinction, dial it all the way up to 11, maximum extinction, and everything in between. So how might variations in extinction intensity affect things? So Rout plotted a curve, an extinction curve called the kill curve. And what this does is it plots the waiting time between events of a given magnitude. How many million years would you have to wait for a 10% extinction, or for 50% extinction species to be wiped out in a catastrophe, or 90% to be wiped out? And we have this curve that Earth forms, but we can imagine other extinction curves. So maybe on Earth, on average, every 100 million years, you get a 90% extinction. So you have to wait on average 100 million years to get an extinction event wiping out 90%. But on some planets, you might get 90% extinction every billion years. You might have to wait a really long time. They're very stable, safe worlds. And on other worlds, the waiting time for a 90% extinction might be only 1 million years. So maybe you have very severe, frequent extinctions, and then everything in between these possibilities. So different kill curves could describe the history of different planets. And we imagine a much steeper kill curve, where we've got this 99% extinction happening every 10 million years, then intelligence just can never evolve. You start getting more complex, you start getting, smarter and working, start experimenting, banging rocks together, and boom, asteroid hits you. And, that just keeps happening over and over again. You just never get very far towards evolving intelligence, and of course, never get to space flight. And it's destroying diversity faster than life can recover and create more diversity and build complexity. On the other hand, we might imagine a very shallow kill curve. Maybe you get 10% extinction every 100 million years, fairly mild extinction events. And maybe on these worlds, evolution stagnates. We have less fit lineages take over and life gets in a rut. Maybe it's just like dinosaurs are there for 1 billion years, and you never get to primates and intelligence without disasters to destabilize things. So what this implies, if you think about it, is it's conceivable. I have no idea if this is true or not, but it's fun to think about. Could there be an optimum level of disaster? We talk about the Goldilocks zone, right? Where the planet is just the right distance from the sun. It's not too hot, it's not too cold, it's just right. What if there is a Goldilocks level of catastrophe? Not so much extinction that it wipes out complex life, but not so little extinction that life isn't challenged, that poorly adapted life can dominate and evolution stagnates. So you don't get stuck at the level of trilobites or dinosaurs. Just the right amount of extinction. Enough to allow complexity to evolve and spur the evolution of complexity without holding it back. It's an interesting thing to think about. So maybe too much chaos and instability is bad, but maybe too little is bad too. As Nietzsche said, whatever does not kill me makes me stronger. I don't know if I totally buy that, but maybe it's possible that whatever doesn't completely eliminate complex life makes life more likely to evolve intelligence. Is evolution, at least up to a point, anti-fragile, that is, benefiting from chaos and disruption? I mean, in the same way that's been proposed that the Black Death helped kickstart the Renaissance in modern science, maybe a bit of disaster and 25 to 50% of the population of Europe dying in the Black Death, maybe that kind of shook up things in a good way. That is one hypothesis. Another interesting thing is if you look at the history of the West, Western Europe and the Mediterranean, they have a remarkably chaotic history. You have empires rising and falling. You have the Greek Dark Ages, the post-Roman Dark Ages in Europe. You have waves of conquest by Egypt and Assyria and Persia and Greece and Babylonia and Rome. It's much more chaotic than China. And is that maybe why technology evolved further faster in the West than China, at least over the past 500 years? You could even argue that we see this pattern in people's lives. Maybe a certain degree of chaos is in some respects helpful. I mean, if you look at Winston Churchill, he had this scheme to knock Turkey out of the fight at Gallipoli in the First World War. And this turns into a disaster. And, huge numbers of people died and it almost ended his career. And Churchill left the government for a while. He spent years plotting his comeback. And when he finally did come back from exile, he saved Western civilization from the Nazis. If you look at, say, Steve Jobs, he started Apple Computer, and then he got kicked out of Apple Computer for being such a jerk. And so what's he do? He goes off. He founds Pixar. He founds Next. And he finally comes back when Apple almost went bankrupt. And then he turns the company around and makes it into the most valuable company in the world. And you kind of got to wonder, what if he succeeded not despite that failure, but because of it? Because it seems like he was genuinely a much better manager when he came back. I mean, if you look like SpaceX, Elon blew up one of the early SpaceX rockets, the third prototype of the Falcon 1, and it nearly bankrupted the company, but it's gone on to become an incredibly successful company. I read a book and it profiled these great stock market investors, and a lot of them had this moment where they lost big. It seemed to be a pattern. You had to fail to learn to thrive. I mean, none of them went completely bankrupt. I mean, that's like life being wiped out on a planet. So none of them went completely bankrupt and went to jail, but all of them lost big at one point, and they kind of seem to need challenge to succeed and need to learn, have some adversity. So I don't know if I'd go as far as saying that anything that doesn't kill you makes you stronger. I mean, polio, for example, paralyze you but not kill you. I don't think that makes you stronger. But I do think you could make a good argument that you need challenge to reach your full potential. I mean, that's why we go to the gym, to challenge our muscles and get stronger, or attend university, challenge your brain. So maybe we need to be pushed in a bit of, and maybe the same is true of evolution at some level. So is the charmed life hypothesis true? My argument here is almost more philosophical than scientific in the sense that I'm not sure how you have a research program studying catastrophes that didn't happen. Short of having the ability to travel to alternate universes where these events did happen in Earth's history, it almost sort of has to be philosophical. But it kind of feels true. Not in the sense of being emotionally satisfying. I think it's kind of an emotionally unsatisfying way of looking at the universe, actually. But my intuition is there's something here. There's something to this that, Earth's history is just so full of these near misses, like the Montpellier or the surviving B-17 bomber. That to me kind of screams survivorship bias. And another thing I find very striking is the way that mass extinction has tended to promote diversification. And even at a personal level, a certain level of misfortune, tragedy, and trauma does seem to make us stronger, and we do seem to benefit up to a point from disasters and catastrophes. So what's the answer to the Fermi paradox? If we really are alone, why are we alone? Well, as I said before, we have these three hypotheses, or at least I have these three hypotheses I'm particularly interested in. Is it possible that Earth-like planets are rare? It's also possible that life and intelligence are just very unlikely to evolve. And it may also be possible that on a handful of worlds where the planet is habitable and life starts becoming more complex and intelligent, most of these worlds are destroyed before that can happen. That their catastrophic events prevent them from ever getting to the point of developing spaceflight and communications and being able to talk to us. So here's the thing. Here's why I think this is not just pure arm-waving and speculation, as I think a lot of hypotheses about the Fermi paradox are. The key thing is, I think there is evidence for all three of these. And if we look back through evolutionary history, for example, we see these key innovations take a very long time to appear. They're not easy to evolve, and they only happen once. And this strongly suggests that things like photosynthesis, the eukaryotic cell, complex animal life, these are improbable events. They might not happen on all worlds. I think that's strong evidence that this hypothesis is correct. Likewise, if we look throughout our solar system and through the rest of the universe, we find very few worlds that look like ours or that seem to be anything close to habitable. Earth-like worlds do seem to be rare. That's not speculation. We can look at exoplanets. We can look at the rest of the solar system. So I think there's very strong evidence that to some degree, the rare Earth hypothesis is correct. Whether Earth-like worlds are 1 in 100, 1 in a million, 1 in a billion, I don't know, but they're definitely not that common. And then the charmed life hypothesis, we see evidence for catastrophe in the history of Earth, in the history of our solar system, elsewhere in the universe. We see a pattern that, to me, seems pretty consistent with some sort of survivorship bias. So I think the evidence points to all three of these being correct. And these hypotheses are not mutually exclusive. Instead, they might kind of reinforce each other and all work together. So all three hypotheses, rare habitability and rare Earth, rare intelligence and rare stability, might work together so that intelligence exists at very low densities, maybe less than one advanced civilization per galaxy will appear. And what if they are all true? What if habitable worlds are 1 in a billion? What if on a habitable planet, evolution to intelligence happens 1 time in a billion? And what if on those planets, 1 time in a billion, will they be spared a severe catastrophe that destroys complex life or just destroys life entirely? So 1 in a billion times 1 in a billion times 1 in a billion. Intelligence might appear on 1 in 1,000 trillion worlds. And if that's the case, we're not just the only intelligent life in our galaxy, we would be the only intelligent life in the visible universe. So, if we are, we better make sure we don't go extinct, right? So do we need to colonize Mars to keep our species safe? I think the answer is, well, yeah, one day. So here's the argument. We can't say that because we've never had a world-ending catastrophe, one won't happen. Our history must be such that no such event has happened in our history, because we're here. But I think what we can say is that even if the charmed life hypothesis is correct, the kind of events that end planets and end civilizations are by their nature rare. They might happen once every 10 million years or 100 million years or billion years. So yes, one day a catastrophe may wipe out the Earth. In fact, if we wait long enough, it will almost certainly happen. But it's probably not going to happen tomorrow or next year or the year after that or any time in the next 1,000 years. So Eisenhower once said, he says, I have urgent problems and important problems. Not all of your urgent problems are important, and not all of your important problems are urgent. Now, obviously, nothing is more important than the long-term survival of our species and life on Earth. But we may have more urgent problems. Super important, but we might not have to worry about tomorrow. Another thing to think about is that compared to the relatively slow-moving pace of these catastrophes that might take millions of years to arrive, it's like this kind of cosmic steamroller, we're evolving really, really rapidly. The extraordinary pace of human progress means we will almost certainly have advanced technologies centuries before the next natural calamity threatens the Earth. So by the time a rogue star appears, we're going to have interstellar travel, if it's feasible, maybe even warp drive. Even if space travel is 1,000 years away, even if planetary colonization is 1,000 years away, we're probably going to fix that before the next big disaster happens. So yeah, I'm not saying space travel is necessarily a bad idea. We shouldn't colonize other planets. But it doesn't have to get done tomorrow. And you could argue, we have more urgent problems down here on Earth. Now, the exception, of course, catastrophes that might have arrived a little sooner are the catastrophes that are caused by our rapid technological evolution. So catastrophes caused by people, those could come quite quickly. So artificial intelligence, robot uprising, genetically engineered superviruses, environmental destruction, nuclear war. All of these become perhaps more likely as technology accelerates. These might happen soon. Maybe not tomorrow, but possibly in our lifetime. So should we go to Mars to get away from all these problems? Well, it's like they say, no matter where you go, there you are. You can't really escape yourself. So my argument would be is that there might be man-made threats that might become a big problem soon, but you can't escape man-made threats by going to Mars because you're taking people to Mars, which are the threat. If we can't figure out how to keep from nuking each other here on Earth, what chance do we have of surviving peacefully on Mars? If we can't tame AI here, how is it going to go any better on Mars? Why won't the Martian AI revolt and kill us all? If we cannot keep Earth, which is a highly habitable planet, habitable, what chance do we have of making it on a hostile planet? It's like they say that the common denominator in all your relationships is you. The common denominator in all of these man-made existential risks is, humanity. So we can't escape ourselves by going to Mars. We're just going to have to learn to deal with these things. So, I admit this is a sort of terrifying way to see life. We're one catastrophe away from the end of everything. Everyone and everything we know of and care about could be wiped out. I don't know, though. There's this idea, the Copernican principle, and it says that, our position in the universe, our perspective is not privileged. There's nothing special about our place in the universe. But there kind of is, because we're here. It's a very unusual place where that could happen. Our perspective on the universe is unusual because there is an intelligent species to look out and see the universe from this point in the galaxy. And we're one of the only places in the universe this could possibly have happened. There is something unusual about our perspective. We are incredibly privileged to be here. And as bad as your day might seem, it could have gone so much worse at so many points. We could have not even evolved at all. Our world has had a charmed life for us to get this far. Think about it. I don't know. Sometimes I think about, risk and all the things that could go wrong, but the universe is full of risks. The planet could be thrown into deep space, and it's been all these mass extinctions. And our species evolved to deal with that and emerge from all this chaos. The human species evolved in incredibly dangerous, lethal conditions. Throughout most of human history, half of children died before reaching 10. Human life expectancy was about 30 or 35 until relatively recently. Violence in the form of murder and intertribal warfare was the most common cause of death for men for most of the past 300,000 years. You had disease, you had starvation, you had droughts and plagues and lions and hostile tribes. And our species evolved to deal with this. In World War II, they would send 18-year-old kids off to be gunners in bombers that were piloted by 25-year-old officers. And they had to fly 30 missions before they could be sent home. And most of them wouldn't make it. That's how dangerous those bomber missions were. But, your ancestors survived all these things. And yeah, maybe that took a lot of luck. But we now live in a pretty safe world, actually. Because disease is less common, warfare is less common, starvation is less common. And so we live in a much safer universe, but we kind of still have these instincts wired for a very dangerous universe. But our average life expectancy is now approaching 80 years old. We live in a pretty safe world. And so I think sometimes maybe we don't appreciate that. And we're so afraid of all these little things, but actually the world's gotten a lot safer, and maybe you should take a few more risks out there. I mean, I'm not saying don't worry about anything. I'm not saying go buy a motorcycle and race that down the highway at 150 miles an hour. I'm not saying, hey, you know what I'm really curious about? Heroin. I want to try that. No, I don't want to touch that. My point is not take stupid risks. My point is the world is now pretty safe. It's less dangerous than you think. And the stuff that gets you is likely something you won't even see coming. So I think about risk taking, and I think, take calculated risks. Avoid catastrophic failure. Buckle up, kids. I'm serious. I nearly got killed in a car crash in the Chicxulub crater, but I was buckled in. But lean into survivable failure. Show courage. Courage is about taking a risk for the benefit of other people. It's risk with purpose. Whatever fork of the road you take is going to have some risk. So lean into that place where the risk is going to come with some benefit for you and other people. If you must assume risk, and you must take risks that have some higher purpose. Sometimes I think about all these catastrophes, and I kind of think about all these little things we're afraid of. Why? Because tomorrow an asteroid could kill us all, but also maybe it'll work out because we are the lucky survivors. 4 billion years of asteroids, ice ages, planetary chaos. We are lucky to be here. Or maybe it's something more than luck. Maybe it's fate, the gods, God, destiny, if you like. Either way, we live a charmed life.